All right, after spending the last week or so talking about image formation, which we discussed exclusively using the Ray model, we're now going to turn to interference and diffraction, phenomena that are associated with waves. And so previously we talked about light as a ray. Now we're going to talk about light as a wave. And then there's even additional phenomena associated with light that you would need to use the particle or the photon model to describe. But we're going to move back to where we started, basically. For 102, we're going to discuss waves again. And so interference is a wave-based phenomena. So any type of wave, whether it's water wave, sound wave, light, interference can be observed. And interference is associated with the superposition of waves. And so I've got this figure from the book here, where on the left I've got wave 1 and wave 2, and you can notice that the peaks and the troughs are aligned. So when those two waves add together, you end up getting a superposition, right? You add each spot of the wave together for both waves, and you end up getting a wave that has twice the amplitude. And again, that's because those two waves are in phase. They're perfectly aligned, peaks and troughs. But if you go to the right-hand side, I've got two waves, and you'll notice that the peaks aren't aligned with the peaks for wave 1 and wave 2, but rather the peak of wave 1 is aligned with the trough of wave 2. And so when you add those two waves together, you get a resulting wave with no amplitude anywhere. And so this basic principle of superposition is how we're going to understand and explain the idea of interference. And so the most famous example of interference was the Young double slit experiment, which was done in the early days when light was just beginning to be studied and attempted to be understood, where there were discussions about whether light was a particle or whether it was a wave. This double slit experiment demonstrates definitively that light has wave-like properties, because interference can only be explained as a wave. Of course, it turns out that light also has particle-like properties, and like everything in the quantum world, all things have wave and particle nature. So those debates back in the early days with Isaac Newton arguing whether light was a particle or a wave, it turns out everybody was right. It was a particle and a wave. So this double slit experiment is sort of exactly what it sounds like. You have a wave. In this case, you have an initial wave that's incident on a screen, and that first screen has one opening, and that generates a uniform wave that's incident on the second screen, which has two separate openings, two separate slits. And those two slits allow two waves to be generated, and those waves propagate and hit the screen, and you can see on the screen that there are alternating regions of bright and dark on the screen. So there are regions where the two waves add together at the location of the screen, and you get a bright spot. And there are spots on the screen where the two waves add together to get zero, and those are the dark positions on the screen. And you can see those alternate back and forth over the entire screen. So this is the idea of interference, and we're going to explore where it comes from. All right, so interference happens. There's that alternating pattern on the screen, but the question is why? And the answer is that the waves that are traveling and hitting the screen, the waves that are traveling from the different screens travel different distances to reach the screen. And that's most easily seen in this figure from the book. Here's sort of a zoomed out picture. We've got these two waves that we're tracing from slit 1 and slit 2, and the two waves hit the screen at point P. And if you zoom in the slit region, you can see that our two waves are going to travel nearly the same distance. except there's this little extra bit of distance that the wave on the bottom of the picture has to travel to hit that spot on the screen. And so the whole idea here is if that distance is related to the wavelength of light in a particular way, we will either get the waves to combine and you'll double the amplitude, or combine and you'll get zero amplitude. And so just depends on that extra path that gets traveled. Now, that extra path, just looking at the triangle here, that extra path is d sine theta. And so if you want constructive interference, if you want the two waves to still be in phase by the time they hit point P, then that extra distance needs to add up to be a multiple of the wavelength. And so this right here, that extra distance d sine theta has to be a multiple of the wavelength. It could be 0, that the two waves travel the exact same distance, and that would be hitting the screen essentially directly horizontal from the screen. But then any integer value, so one wavelength, two wavelengths, etc., that will result in constructive interference at the screen. Now, if you shift the wave, but not by a full wavelength, but a half wavelength, then you'll get destructive interference. So rather than the peaks and the peaks aligning, you'll get a peak and a trough aligning, and that'll result in no light hitting the screen at that particular location. And so we account for that with the m plus 1/2 times lambda. So that will be integer multiples of the wavelength, half integer multiples of the wavelength, or integer multiples of the half wavelength. So that extra path traveled now, instead of a full wavelength, is just a half wavelength, and that shifts the wave exactly by the right amount to destructively interfere with the other wave. And so m here is known as the order, right? So the 0th order, the first order, etc. And so if you were to shine light through the double slit, you would end up with this intensity pattern on the screen where you get a bright central peak, and then you get peaks that diminish in intensity as you move out in a characteristic sort of fading fashion. The last thing to mention is if we have more than two slits, if we have 3, 4, etc., what ends up happening? Well, if you have additional slits, what you end up getting is you get, notice in this picture, I've got 2, 3, and 4 slit examples. So this is light being shown through 2 slits, 3 slits, and 4 slits. You'll notice that as the number of slits goes up, I go from purple to red to blue, just focus on this central peak. Notice that the red peak is narrower than the violet peak, and it's a higher peak. And the blue peak is even higher and even narrower. And so as you add more and more slits, the central primary peaks get higher in peak value and narrower. The other thing that happens is you'll notice you get secondary peaks as you add more slits. You'll see with 2 slits you don't have any secondary peaks, but with 3 slits we have 1 secondary peak, and with 4 slits we have 2 secondary peaks. And so with 5 slits we would have 3 secondary peaks, and so on. And so the addition of more and more peaks results, or more and more slits results in a sharper, narrower, more intense primary peak with the addition of more and more secondary peaks.